Okay, so good evening, everyone. Welcome to this problem solving session of the NPTEL course on compiler design, which is taught by Professor Santanu Chattopadhyay from IIT Kharagpur. I am Saurabh Sharma, PMRF scholar at IIT Patna and PMRF TA for this course. So let's wait for 2-3 minutes. Let me wait for some other students to join. Otherwise, we will get started. First, I will say there is some network issue in my college today, so there may be problems listening or when I change the slides. So in that case, just comment on the comment section. I will again detail that. So I think I should get started. So in this week, week 11 of this course, uh, that is totally dedicated for intermediate code generation, which is optional part of compiler design. I mean optional phase of compiler design, in which the major focus is to generate a reusable code which can be relocated to any other device and which can be reused again. So it comes after your that parsing part, semantic analysis, semantic analysis. So in today's lecture, I will first go through the lecture slides, then some previous year questions, and after that, if there will be more time, I will take some other questions of this topic. So let me share my screen. I think, yeah. So in week 11, the things started from miscellaneous statements. So uh, means, which kind of statements we can use during parsing, and after that what code it will generate. Then there are intermediate code generation part, in which the main code that is generated is the 3 address instruction code, in which we actually implement 3 address instruction code. How? There are multiple methods. The method which is actually told is quadruple representation. There are many more. I will tell if time will allow. So in this, each instruction has at most 4 fields. First is operation, there are multiple operations plus subtraction or go to or any other. Then there are two operands, uh, means uh, there may be on which the operation will be applied, and also we can assign a bit that can indicate whether it is a constant or a pointer, and then a destination where we will store the output. So like in this case, there is x is equal to y plus z. We have x as destination, we have y and z two operands, and we have operation plus. And in SRC 1 and 2, we can actually provide a bit which can actually indicate whether it is constant or a pointer. So it may be a pointer, it may be a pointer to that address, it may be a constant. So how we can change? We can just assign some value 0 or 1. If it is 0, then it may be a constant, otherwise it is a pointer, or vice versa we can. Okay. Then there was an example like if we are given such a statement. So if x is equal to if x plus 2 is greater than 3 into y minus 1 plus 4, then z is equal to 0. So how we will go? So first we will check for the statements. We will store the values which are actually variable and which may take values to some temporary registers or temporary variables here. So first we store the value of x plus 2 and y minus 1, and then we have to check for uh, the broader block, or we can say 3 into y minus 1. So we provided another variable, then we have to add 4, we provided another temporary variable. Now we have to apply some of the uh, conditional statement. So we applied it. If t1 less or equal to t4, go to L, where L is something label or something which we have to means execute as a task, and that is actually set of statements. And otherwise, if we will just eliminate t1 less or equal to t4, what will remain? This condition only. Okay, because it is t1 is greater than t4 if we see here carefully. So if that doesn't happen, go to L, otherwise we have to go for z is equal to 0. Okay, then there are some operations which we can apply during 3 address code generation. So one of the most important operation is assignment. So for assignment, the grammar is like this. We have a start symbol which tells id equal to e. Then there are some operations where e produces e plus e, or all the operations which can happen on that e. Okay, and finally there is id which actually takes the value. So uh, correspondingly, we can say they have provided grammar rules for semantic actions. Like in first, there is s produces id equal to e. So what will happen? Uh, what we actually want to tell? We want to tell that where id dot place is equal to p dot place. Means the value we have stored at place of e, we have to assign that value to id. So like if we go through some attributes of non-terminal and terminal symbols. So attributes of for non-terminal e are: first is there is e dot place, the name that hold value of e. So where we will tell about the place, we are actually interested about the place where we are holding the value of e. Just a second. Chandana, I can't comment about exam here because we are not connected to that exam conducting part of NPTEL. You can ask in discussion forum for that. I'm just here for problem solving session only. We are not provided any information regarding this. Means me and any of the PMRF TAs. You can reach by discussion forum. So returning to the attributes, there are two attributes. First is e.place, then e.code. E.place is the name that holds the value of e, that non-terminal, and e.code is actually sequence of the three address statement corresponding to evaluation of e. Means what we want to evaluate, we will actually perform in that sequence of three address statement when we will tell e.code. Similarly, for s.code, that also indicates the sequence of three address statements, and then for terminal, symbol id. So id.place actually contains the name of variable that has to be assigned. So if we are telling x is equal to y plus z, so id.place will actually contain the name. Like if we are interested for y, so it will contain the value of y. Okay, the name y. Okay. Then there are some functions. Function new temp return a unique new temporary variable. So for each of the value stored for e or s or any other thing, new temp actually creates a temporary variable, and then gen actually accepts a string and produces its three address quadruple, and this parallel sign actually concatenates to three address code segments. So using this, if we see this table now, it is very simple. So if I am telling s produces id equal to e, so s dot code, the semantic action, how we will write semantic action? First we will write what s want to do using three address code. So we will write s dot code. It will tell the sequence of three address statements. S dot code assigns e dot code. E dot code means the uh, E dot code means the statements, three address statements, which are actually we going to assign by uh, means for E. Then what we want to do, that we will tell using gen function. So we have now three address codes. First is for S, and then we want to concatenate it using there is uh, network issue. Okay, so here what we want to do, we actually uh, want to use that code id equal to e. So what we will do, we will concatenate this id equal to e using concatenation symbol. Then we will generate the string which will produce the three address code. So we will apply gen, and what we want to do, we want to apply id equal to e. So the values we are storing, that is stored at place of id symbol, that we want to take that from e dot means the value of that variable e. So what we will do, we will assign e dot place to id dot place. Similarly, if we are given some operators like e1 plus e2, so what we will do, e dot place for e dot place we will actually create a new temporary variable, so we will call new temp, and then what we want to do, we will tell the compiler that we want to write some code, some C address code for these uh, for these variables. So we want to write some code for e, which is actually related to e1 and e2. So we wrote it, e dot code is equal to e1 dot code, that is concatenated with e2 dot code, and what that will generate, it will generate actually the value that is actually contained by e1 and e2, that will be added. So e dot place, that will hold the value of e, that will be assigned to the values of e1 dot place plus e2 dot place, means e1 and value at e1 and value at e2 will be added together, and that will be actually provided to e dot place, or the value of e will be that only. Similarly for e into e2, then there is minus e1. So minus is actually, or subtraction is actually unary symbol. So for that we will just write u minus and e1 dot place. Okay, so we don't have to do more things, we have to just assign three addresses, so 1 2 and 3, and here we have only two addresses, e1 and similarly we have just value of e1, so we can write it like this only. So e1 dot place, e dot place is equal to e1 dot place, and e dot code is equal to e1 dot code, and then for id may be empty, so we have id dot place equal to this, and we don't have any code, means we don't have any variable which has some three address statements to be performed for this, so we are just making it empty. So for this example, if we just consider, we are not considering anything about uh, ambiguity or any other things, any other complications for grammar. So we are just considering the compiler is smart enough that it can take care of all these things. So we are just interested about how we will generate its parse tree, and what action we will produce as uh, semantic analysis part, and also how we will write the three address code for this. So what we will do, if we see this grammar, we have starting symbol as s, so the parse tree will start from s, and using that parse tree we will just generate these things. So what we will do, we will go one by one, and if we will use lr parser, it will go from bottom top and reverse of rightmost derivation. So what we will see first, reduction, what will be done, will be e derives id. So id will take the value of uh, the actual literal there. So in this id dot place will be taken care by y only. So what id will hold, it will hold the value of y. Okay, similarly for z also, for w also, and for v also. So we will start from this e derives id, then we will perform e derives id for z. Now we will perform e plus e. Now what it will generate, it will generate this y plus z. Then we have unary operation w on w, that is minus of w, so u minus of w, and then plus v. So till 8 we are done with the first layer. Then we have to perform the we have to take both into bracket, so we have done it, and then multiplication, and then assignment operator. So all of these things will be like that only. So Now if we will write the code for this, what we are doing in first action, in first action or first reduction, we are taking value y and we will assign it to the place of e. Okay, so id is actually taking the value y and we have assigned that value to the place of e. So e dot place is equal to y. Similarly for these two, we have e dot place is equal to z. Now what we have to do, we have to perform addition operation over that and we have to store it to e. So what we will do, we will first just calculate calculate the addition and we will store it to the place of e. Before that we have to create a new temporary variable. So we have called new temp and with the help of that we have created some new temporary variable t1 and we have stored it to place of e. Now t1 will hold the value of y plus z. Okay, so uh, what it will perform, it will perform actually y plus z, that will be holded by the place of e, and the place of e is actually now holded with the help of t1. So t1 uh, is actually equal to y plus z. So t1 will hold y plus z here, and similarly for fourth uh, action perform is actually e is equal to within bracket e. So for that, if we see, we have this operation e dot place is equal to e1 dot place and e dot code is equal to e1 dot code. So we have performed it similarly. E dot place is equal to e1 dot place. So even here we have e1 as e only. So e dot place will be having the value what e has, that is t1, and the code it is holding will be similar as the e dot code that is there. Similarly for w and u minus, and at last what we will do, we will just assign the value as code is equal to t1 y plus z and t2, and likewise we will perform this overall statement that is actually covered in the week's content. Then comes the code generation for arrays. So it is different because we have to hold some number of values in the list. So what we will do, we will just consider an array element ai and we will assume the lowest and highest indices, uh, and based upon that and the base that is actually uh, depends upon the language, the programming language we are using, we will actually uh, calculate that highest and lowest indices, and then first part of expression can be pre-computed into constant and added to offset of I to w. So some mathematics, how we will calculate the uh, for two-dimensional arrays. Now this is the grammar we will use, we generally use, that may be differ in case of different languages. So the basic grammar that is used is uh, like this. We have s derives l equal to e, then e plus e within bracket e and l, and l is for completing the list, or there may be some value, and e list is actually uh, number means the name of that array and the starting string, or some a list or different array. So the attributes one by one I am covering. L dot place actually holds the number, the name of variable, maybe array name, and L of offset is actually offset of the element for array. So where we want to start the array, that is actually offset, then means location of elements of array. Then e dot place, like previously, holds the name of the variable holding value of expression e. Elist dot array actually holds the name of array referred to, and place actually is the name of variable that holds value for index expression. Then there is dimension, means which current dimension we are considering for array. Then there are semantic actions, so where we will write this asterisk L is equal to E. There what we want to tell that if L dot offset is null, then we have to perform this assignment operation clearly, like in previous case L dot place is equal to E dot place. In last case we had E dot place is equal to ID dot place. Else if we have offset, means we have offset, then we will start from that offset, like we are starting the array from fourth position. By default, if we are writing array of size 100, we just consider the indices from 0 to 99. But in this case, what will happen if we are starting from 4 up to 95, so the offset will be 4, and we will start from 4. So L dot place, and within that we will refer that offset, and we will actually assign the value of E dot place to that L dot place, and provided that offset only, means like a of 4th we want to assign some value 100. Okay. Then if we want to add, then what we will do, we will just create a temporary variable, and then we will emit the uh, operation of uh, addition. Then if we are just assigning the value, means storing the one array to another, or we can say copying the element, then we will do like e1 dot place is equal to e dot place. Actually, there is maybe problem. Let me close my lights. So hope I am visible. Uh, there are too much images, so I have to close my lights. Okay. So some other semantic actions are like if we are writing e produces L, then there is L dot offset. If there is no offset, then means we are doing some alteration of this one. So here we were storing E to L, here we are storing L to E. So we will just create a new temporary variable, and we will store that value of L holded at that place to E dot place. Then L is ID is simple. If offset is null, we have to just place that uh, value of ID to the L dot place or place of L. Okay. Yeah. Then we have completion of list. So for that, these are the actions we have to just provide the place, uh, to e dot list, he returns the constant part of array. Then what we will do, we will take a constant part and we will just end the array. Okay, and here we want to just provide a different array, and we want to start some array. So we have id which has some value, and we want to start array. So like a, if we have array a, then we start with the means, some value like a having 10 20. So a within bracket 10, then uh, within means we start the bracket and we will write 10. Then again we will go to e list, go to this one, so 10 comma 20, and if you want to then close here, so we will ask this one. So we have e list, we will close with this. Okay. Like this, there is an example. It is actually told in a class in very good manner. Similarly, how we will generate the code, and then there is Boolean expression. For that, what we will do, we have some attributes of Boolean expression b. So b dot true defines a place where control should reach if b is true, and if b is false, we want to take the control, then b dot false will be told. Then if we are given some binary or unary operators, how we will perform it? So assume true and false transfer points for entire expression. So if b is true, we need not to evaluate for b, then called short circuit evaluation is called short circuit. And if b is false, b2 needs to be evaluated. So b1 dot false assigned the new level marking beginning, and then new level generates a new level. So like here, if we have this b1 or b2, if b1 is true, then b is true. We will assign b1 dot false to a new label, and if b2 is true, then b is true, and if b2 is false, then what happens in case of b1 or b2? If any one of this is true, then it will true. Okay, so b dot code will take like b1 dot code. If it is false, then only we will go to b2. Okay, so b dot code, what I want to tell, b dot code will actually assign true if b1 is true. Otherwise we have to means we have to check for b1 is false or not. If it is false, then only we will move to b2 dot code. If it is false, then it will be false. Okay. And for and, what we will do, if we are having b1 dot false, just reverse of that. If either of b1 or b2 is false, then it will be false. So if we are taking b1, and we have to then check for whether it is true or not. If it is true, then we will go to b2 dot code, whether it is false or not. Okay. Similarly, for not b1, if it is false, then b1 is true. Sorry, if b1 is false, then b is true. If it is false, then b will be false. Sorry, means if it is true, then b will be false. Then there is absolute value. So if it is true, we have to just return true. If it is false, we have to just go to b dot false. And if it is any relational operation like written here, so if id dot place relational operator id2 dot place, go to b dot true, and then generate go to b dot false. So in Boolean expression, we have to just search for whether it is true or not. Then there are some disadvantages makes the scheme inherently two-pass procedure, because we have to just take the values and then pass it. Then all jumps targets are computed in first pass, and actual code generation done in second pass. Okay, so means what we are doing, we are just taking some value, we have to generate some temporary variables or the targets, and then we have to actually based upon target we have to pass the values to that target. Okay, fine. So inside single pass approach that can be developed by modifying the grammar a bit and introducing a few more attributes, a few new procedures, quadruples. So there are attributes like b.toList. It is actually list of locations within the generated code for b at which b is definitely true, and similarly for false, if b is definitely false, it will generate the list of locations for b. And when it is once defined, all these pointers will be transfer control to b.true, and similarly for false, we will control a transfer to b.false. So instead of b.true or false, we will create a list. Okay. Now there are some extra functions which we can use. There is make list, merge list, backpatch, and next part. What make list does? Make list actually creates a new list of a single entry I that is actually an index into the array of quadruples. Okay, so it will hold the index of array of quadruples and make a list. And merge list actually merges two lists. If we are writing L1 and L2, then L1 will be merged with L2, and N will be followed by L2. Then there is backpatch, which actually inserts the target as the target label into each quadruple pointed by entries in the list. So it actually what it does, in one line we are just inserting a target as target label for each of the quadruple. Then there is next quad, which returns the index of next quadruple to be generated. So one quadruple is generated, we have to go for next. So the modified grammar of that previous one will be like, if we are given v1 or v2, we will write it like b or mb, where m is actually dummy non-terminal with the attribute m dot quad with that whole index of quadruple, like here. Okay, so wherever we have b for or and operations, we wrote it as mb. Now consider this rule v1 or mb2. What it will do, before the reduction of b2 starts, reduction m dash epsilon has already taken place, means it is not having anything. So m dot quad points to the index of the first quadruple of b2. So it is actually list, and in this is actually points the first record. Okay, like with the help of this one. So what it will do, it will just backpatch b1 false list and m dot quad, and it will merge list of both, and then check for false list. Okay, then for here what we will do, it will just check against the previous one, like it will check for b1 dot true list with m dot quad. Okay, so each of the records in b1 will be matched with the records of b2 or list of b2, and then if it will be at false, it if in case of AND, if b1 is true, then we will go for b2, and we will merge the false list of it. Then there are unary operations and assignment operations, that is very simple. Then if it is true, we will create another quad list which is having only true values and for false we will create for false also, and this is actually for empty. And for relational operation we will just create the list for both, means for true and false, and we will just apply the operations like in previous. Like here what it will do, it will start from B, and like in previous case x is greater than y, so id will take care of x and this id will take care of y. We will perform the relational operator. Then from here we will take m is e, then 3 4, and likewise we will just first traverse with this, then this, and then this, and then apply not, and then at final we will perform OR of this. So what transition will do one by one. So here we had greater operation, so we will just perform this operation, like if we have x is greater than y, go to somewhere, otherwise go to somewhere. So if there is true list we have to go somewhere, otherwise if it is false it will go to somewhere other, likewise. Then there are control flow statements which actually tells about how the control will flow throughout the code. Okay, so if there is assignment, is assigned some expression to a variable. If then else, actually control flows either of one part. In while do, the control remains within some part whenever there is a condition that is true, and if there is some block of statement like there is label, then it will run then from begin to end. That is actually a block marker. Then there is grammar for it. There is next list, which actually is list of quadruples containing jumps to quadruple following s, and l dot next list is similarly as s. Then there is no terminal n that enables to generate jump after then part. So these are the transition rules like that only. For there is some m which is actually initially at epsilon, and for n also. So if b then ms1, then we will just check whether b is true or not, and then we will merge list of these two, uh, b false and s1 next list, and similarly for if b then m1 s1 and else n2 s2. So for this we will check for both conditions, and for block means for loop statement we will backpatch to s and n. So these were some slides from previous year, uh, sorry, from this week content. Now we'll go through the questions of this week. Then we will, if there will be time, I will try to go through some other questions of this. Again, there is. Let me share with. Let me share on the screen. There is internet problem also. Sorry for that. It's not in my hand. let me connect to the marker device. So we have some previous year questions. Okay, so we have previous year questions. So the first question is, for the rule B produces B1 and B2, the operation B1 dot false is equal to B dot false requires two passes as B1 dot false is not known, B dot false is not known, both B1 dot false and B dot false are unknown, or none of the options. So what will happen here? Oh, there is again network issue. Okay, let's try it. Okay, so in first question, we are given a production rule B1 and B2, and we had B1 dot false is equal to B dot false. That requires two passes. Why? Because B1 dot false is not known, or B dot false is not known, or both are not known, or none of the options. So clearly, what we check here, we first check whether B1 dot means B1 is true or not. If it is true, then we actually go for checking the false for B2. So B1 dot false is there. B1 dot false is equal to B dot false. It actually requires two passes because B1 dot false is not known. Okay, that will actually determine what uh, okay. So what will happen here, if B1 dot false will be equal to B dot false, that will actually require two passes because B1 dot false is not. Okay, so answer is A. Then there is for 3 address code generation, the rule as derives, while M1B do M2S1, B dot fastness is backpatched with. Okay, so what will happen here? So B dot false is actually can't be backpatched for 3 address code because rule S uh, because sorry, for 3 address code generation of rule as derives while M1B do M2S1. So B is actually the condition. If there will be some condition that will be true, then we will go for the list of S1 that will be executed. So B dot false list is backpatched with, not with m1 dot quad or not with m2 dot quad, because m1 dot quad is for B, and m2 dot quad will generate the next quad for S1, means the set of statements which are actually meant for uh, need to be executed when B is got true. So there is no use of B dot false list here, so that cannot be backpatched at this point. So answer will be, oh sorry, C, not B, C. So let's see. It will be C. Then in third question, in rule B derives B1 or MB2. The non-terminal M is used to remember the start address of B or B1, B1 and B, or none of the options. So what I discussed earlier, we have B derives B1 or MB2. So initially M gets epsilon, and it points to the start of list of B2 here. So again, when it will get executed, it will traverse through the list of B2. So not B and B1, it will be B2 only. So answer will be D here. Okay. So B derives B1 or MB2. Actually, uh, not remembers any start of B or B1. So answer is D. Then in 3 address code, arrays are not supported one dimensional, more than one dimensional, or supported via pointers. So two people are joined. You can comment on this. It's very theoretical question. So if you want, you can write on chat. I'm providing you 1 minute. If you have gone through the PPT, it's very simple. Okay, so I'm writing the answer. Answer is actually B. Arrays are one dimensional in 3 address code. Then there is the fifth one. In the rule, S derives if B, then MS, N, else MS. N is used to generate a jump after then part, else part, both then and else part, and last is none of the options. Just a second. Sorry for interruption. Oh, okay, correct. Okay, again starting. Question number 5. Sorry for the interruption. So in the rule, S derives if B then MSN, else this MS. Uh, so N is used to generate a jump after. It is also theoretical question. So if you want surface, you can just comment the answer. It is covered in the content also. I have also covered before taking the question. So the answer is actually A. So M is for taking the set of statement for S, and N is for 10 part. So then for next one, for Boolean variable B dot true list contain. It's very simple one. List of locations at which B is true, or list of locations to jump to if B is true. Then list of locations at which B is true and the locations to branch to. Then none of the other options. So it's very simple one. I have also covered in during when I was covering the week content. So it is A. Okay. So B dot true list actually contains the list of locations at which B is true. Then there is some problem. Okay. Now, so for 3 address code generation, B derives B1 or MB2. M code is used to backpatch. It is also covered. So what M dot code is used to backpatch B1 dot true list, B1 dot false list, B2 dot true list, or B2 dot false list. So what it will backpatch? It will actually backpatch the values of B1 dot false list. So if B1 is false, if V1 is false, then only we will traverse to B2. So it will actually take care of B1 dot false list. Okay. So it's B. And the last one, for 3 address code generation of rule S derives is simple. No problem. S derives while M1B do M2 S1. The non-terminal M2 is used to note loopback address or backpatch B dot true list or backpatch B dot false list or none of the other options. So what it will backpatch? So what we will do when it will try to run means this S1, then this B will be true. So that will be the answer, that backpatch B dot true list. If B is true, then S1 should execute. Okay, so answer is B here again. Okay, so that's all for previous year questions. We have 1 hour left, so I will take some other questions. So for this, if there is any doubt regarding this week or previous week content, what I have taught and what is covered, so next week is the last one, last problem solving session. You can ask through that discussion forum, or you can use YouTube comments. You can comment on the videos I have taught, and you can get back to me using this problem solving session, which has last edition in means last lecture in next week, means on Tuesday. So first I should save it. that is all for previous year questions. Now I will take some other questions. So I have very less bandwidth, so I think I should stop my camera. It is recording, so the recording will be uploaded to YouTube. So camera, I am just knowing the camera device, and lectures I am recording myself here using software. So just one device for keeping the bandwidth of it works. First, I will provide a gist of what happens when we have 3 address port. So, yeah. Okay. That I can okay. So we went through representation of 3 address port. Okay. So we went to quadruples. There are 2 more. I will not go to depth. I am just introducing it. So there are quadruples. There are triples. There are indirect triples. So in quadruples we have 4 things. We have operator, we have operand 1, operand 2, and then result. Then in triples we have only operator, operand 1, operand 2, and in case of indirect triples, some address 2. triples. Okay, so we went through quadruples. So I'm taking very small example how we store it. First, how we'll store it. Okay. So, for example, we are provided some statement like a plus b into c by e power f plus b into a multiplied. Okay. So first we will write the address code. For it. So three address code for this will go like, we will first go through the priority or precedence of the operators. So let's provide first precedence to this power. Okay. So T1 will hold e to the power f, then T2 will hold v into c, T3 will be equal to, now we have this, we can apply this T2 by T1, then T4 will contain b into a, then T5 that will contain a plus T3, and then T6 you will take T5 plus T4. Okay, like this. It's a very simple example. There is no rocket science. So what we will store? Location, then there is operator, there is operand 1, there is operand 2, there is result, so there are total 5 and total 6 operations. We will go from 1 to 0 to 5, 3, 4, 5, then operators, like this, then operator 1, operator 2F, T1, B, C, T2, T2, T1, T3, B, A, T4, A, T3, T5, T5, T4, and T6, like this. Okay. So if there is some unary operator, we will just use one operator field, and operator 2 we will just leave it. Okay. We will not use this. Okay. That is one thing. Now we should go for other examples. So example 2, this was example 1. So like we are provided some statement this into c, no, b into minus c. So first what we will do, we will prioritize the unary operator like this. Okay, so we can store it like T1, then U minus C, then T2, B into C minus of C, that is T1. Then we don't have to optimize it, we are just going one by one, otherwise we can reuse it without optimization. How we will do, I am just telling that. 4 B into T3, T5, T2 plus T4 is equal to T5. Likewise. Okay. So in quadruple, what we will do? We will write like location, then operation, then operand 1, operand 2, then result. We have 1, 2, 3, 4, 5, 6 statements. If I am not wrong. We can start from 0, we can start from 1. So there is operator that will be U minus, and 1 will be C. We will store at T1. Operator 2 we don't have, we will just keep it blank because we don't have any operator in case of means second operator in case of unary operators. There is second, we have multiplication sign B, T1, we will store it to T2. For 3, multiply B, T3, then there is B attack, T3, and we restore it to T4, fifth statement, T2 and T4 we restore it to T5. Then remain the last one. We have assignment operator on T5, restore it to A, like this. Then I think should go for control flow and Boolean expressions. We have 45 minutes, around 45 minutes left. Okay, so let's go for control flow. Okay. So what happens? Uh, what I have earlier told that Boolean expressions are typically used along with the if then or if then else or while do statement constructs like oh there is again the problem. I hope it should not reflect not so for example what I was telling that Boolean expressions are typically used along with if then or if then else or while do statement constructs. So if consider there is some grammar it is like s derives if e then s1 or if e then s1 else s2 or we can say while e do something s1 or do s1 while e likewise. So here two things I want to say. There are two things like entry control statement and exit control statement. So entry control is actually while loop and exit control is do loop. Why? Because we provide some statement in entry to be checked and here for exit. Okay. And is actually Boolean expression evaluation. Okay. So E corresponds to Boolean expression evaluation. Okay. This should be converted to 3 at this point. Okay. It should be converted to 3 at this point. These are the things we should take care of. So what happens if there is consider if there is if then statement. Okay, if there is if then statement, we have two things. We have a label then we have a control flow. Okay, so on which level where the control flows would go. Okay, so in starting we have e dot code. So it either point to e dot true or e dot false based upon the condition provided. So either to e dot true or to e dot false, and for label e dot true and for label e dot false, it will execute some set of instructions. Okay. The flow is like this. Okay. So what is SDT or syntax directed translation for this if then? Like I have earlier told, we have their given production like S derives if E then perform S1. So the semantic rules corresponding to this will be on E dot true we will start with new label. On E dot false we will execute the next string. Then S1 dot next will perform S dot next, and the code will be depend upon E code of E, and if we will check for true, otherwise we will go for S1 dot code. Okay, this is like the control flow. This is for simplest one. So there are multiple rules for if then else, also for while, for loop, for do while loop. Just a second, there is okay. So let me go for each of these. For if then else, then for while or do while. For so for if then else statement can happen. So we will start from a dot code. We tell whether it is pointing to a dot true or to a dot false. Then if it is a dot true, we will execute s1 dot code. Then we will go to else dot next. If e dot false, then s2 dot code, then s dot next. Oh, no. This is label. No, no, okay, okay. This control flow, this label. Now, if we have e dot true, we will execute s1 dot code and then go to s dot next. Okay. Then if e dot false, then s2 dot code. Then there is s dot next, which will be pointed with this, like this. Okay. So what will be the detail for is for this we have production, just like s data is if then s1 else s2 corresponding semantic rules so for e dot true and e dot false, for both we have new label. This one dot next is equal to s dot next. Dot code, dot true. Then we will check for s1 dot code. Then we will go to s dot next. Then go to check e dot false. There is problem. sorry for that. I'm just putting it again. Like this. Let me save it first. Okay, nice. Good. Now we can go to the next part, that is while loop. For this we will have again label and control sheet. Let's start begin. We will execute some code. We go to v.true or v.false. v.true is equal to s1.code. Start begin. v.false. Then stt equals to v-stt. Semantic rules. Then for do while, so what is happening here? We will first uh, do the things, then we will begin, or we will check for the statement. Okay, like this. Okay. So in while, what we were doing, we were going from s dot begin to e dot port, then checking the condition, and again go to s dot begin. From here, we are starting with code, and at last we are going for s dot begin. That is what I want to say. Now, coming to the some of the questions. Okay. For example, we are given a question like A is less than B, or C is less than D, and A is less than F. Okay. So and the path we are just provided the previous grammar. E derives E or E and E, and E derives false or true, and likewise. So how we will proceed? We will start from creating the parse tree. So E derives E1 or E2. Okay. So E1 is having something like ID, veloc ID. Okay. Then E2 is having E3 and E4. There also we have ID, relog ID, ID, relog ID. Different values of E is for just differentiating values. So this ID will take care of A, this relog will be less, this will be B, C less than D, E less than, like this. Okay. So what we can infer from here? We can infer like this. If A less than B is true, then E is true. If A less than B is false, then evaluate E3. If C less than D is true, then we have to check for E4. Okay. If E1 is true, we are not going anywhere. E is true again. Okay, because the anyone or one or anything will be one. Then if it is false, we will go for E2. E2 is having E3 and E4, so we will check for E3. E3 it is also end with this E4. So if E3 is true, we have to check for E4. That should also be true. So if it is true, we will evaluate for E4. If it is false, then is false. Okay, like this. So if you like want to write its interpretation, we can write it also. Dot true is equal to E dot true. Then we will write false label for E1, then true label for E3, then E3 is false, E2 is false, and E is false. Okay. Then if false true is true for E, and if false false is false. Okay, so any one of these will false, will actually uh, false if E1 is false. Okay, if E1 is true, then we don't have to take care of anything. That will be true again for everything. Okay, if we revisit it, we can write it like if A less than B, go to L dot true, then let's go to L1. L1 will check the C less than D, then we should go to L2 or go to L dot false, L dot true will take a temporary variable and assign it to 1, and L dot false will take that variable and assign it to 0, like this. Okay, so we can write in case of memory locations. So like we are starting from memory location 100, we are storing it as A less than B, go to 103, T1 is equal to 0, now go to 104, so 101, 102, 103. In 103, what we will do, we will check for C less than D, then go to 107. I wrote something wrong, just a second. To 104, 103, T1 is equal to 1, 104. If C less than D, go to 107, then again T2 is equal to 0, go to 108, and again T2 is equal to 1, so 5, 6, 107. Okay, so it is true, then T2 is true. Then we go to 108, in 108 we will check for if E less than F, go to again plus 3, 111, T3 is equal to 1, 33 is equal to 0, then go to 112, T3 is equal to 1, 09, 110, 111. So in 112, what we will do, if T2 is equal to T4 and T3, and at 113 we will store, sorry, T4 is equal to T2 and T3, and T5 is equal to T1 or T4. Okay, so this is for AND and this is for OR, like this. Okay. So in this way we can write any of the CSS code and what it will and the flow of the code that we have told. Okay. So we have less than 8 minutes left. Let me check if I have some question for till time. So we can enter some situations of previous code only, like we can write it as if we have a question given as p less than q and r less than s, or t less than u, or we can write it like a b c d e f, a less than b, c less than d, e less than f. Okay, so what we will do, till this triple one we will go same, and for 112 and 113 what we will do, 112 and 113 we have to update the code. Okay, so 113 we had this and then or. Okay, so T4 will be T1 and T2. Oh, sorry, T1 and T2. Here we went for T2 and T3. So T2 and T3 are basically for these two. So now we will go for these two. Okay, so T1 and T2, and then T5 will have T4 or T3. Okay, so T4 will be having this and T3 will be having this. Okay, so this way we can go for such question. And again, if we are provided something like a less than b and c less than d and e less than f, so we can go either ways. So we can just write like till 111 it will be same, till 112 it will be t4 and t5, 3. So what we will do, we will just write t1 and t2 and t4 and t3. Okay, there will be not much thing we have to do in this case. And if we are given something like a less than b or b less than sorry, c less than d or e less than f, then we have to just put or, and till 112 it will be same, 111 and 112 and 113 will be t4 equal to t1 or t2, and t5 will be t4 or t3, right? Okay, so this way we can write any CSS code of any expression. I think I missed for loop. So for loop we can consider while loop. Okay, for a for loop, because it is also just does the things and then check the condition, and then again means checks the condition and does the things and again. Okay. So what you can write a for loop, maybe considered as a while construct to generate readdress. So like this. So first save it. So in today's lecture, I actually uh, tried to tell more about what we have went through in week 11, which was basically for intermediate code generation. So at first I went through the representations, then yeah, the control flow analysis, some question on that, how if then else and while do and do works, and how can we work with this. And in previous year questions, we have solved some on backpatching and free address code and true list and all. So thank you for who have attended earlier, and this is all from my side today. The slides will be shared after this lecture only, and I request all to just tell your problems or anything related to this course to discussion forum and comment section of YouTube, because next week is the last lecture of this session. So I want that every one of you come up with your problems which are not yet covered till now through this lecture, or the content if any. So thank you all. We will meet next week, same day, same time.